Hi guys, today we're going to talk about generalized SRv6 or G-SRv6 for short. In SRv6, a segment ID is a 128-bit IPv6 address associated with a segment. As such, SRv6 supports to carry a seed list with multiple seeds in the SRH to instruct packet forwarding, and this is the basic principle of SRv6. Currently, in most scenarios, SRv6 is mainly best effort traffic without SRH, or TE traffic with less than 5 Cs. This means that the SRv6 header overhead is under control and acceptable. However, in scenarios where the number of Cs exceeds 5, such as TE or SFC scenarios, the SRv6 header overhead may be high. For example, if a SRv6 packet with 10 Cs, the following problems may occur. Low packet transmission efficiency. So the too big overhead will affect the transmission efficiency of small packets. Reduce hardware forwarding performance. If the seed list contains a large number of seeds, the size of seed stack may exceed the parsing window size of chipset, meaning that the hardware must perform a recycle, which will affect the forwarding performance. So to address this issue, generalized SRv6 is proposed. In an SRv6 domain, seeds are allocated from an address block, we call it as seed space. So they have the same prefix. For this reason, one seed list may carry multiple common prefixes and other identical information, meaning that the compression is possible. For example, the prefix A:/48 is used as a seed space in an SRv6 domain, and the total length of the node ID and function ID fields is 32 bits, and the argument and padding fields occupy the remaining 32 bits, which are all set to 0. So for seeds in the seed list, the first 48 bits and the last 32 bits are all redundant, while only the 32 bits node ID and function ID fields are variable. In this way, we can avoid to carry multiple, redundant information in seed list to reduce the overhead of SRv6 packets. So this is the basic principle of SRv6 header compression. So the main idea of G-SRv6 is to delete the redundant information, such as the common prefix from the seed list, and carry only the variable information like node ID and function ID, so thereby achieving packet header compression. The variable part is called a compressed seed, C-seed, or generalized seed, G-seed. To better understand G-SRv6, we define G-seeds, which can be a single 16-bit or 32-bit C-seed, or a single 128-bit SRv6 seed. We also define a G-seed container, which is a 128-bit space that the segment left field points to in an SRH. So the G-seed container supports to carry multiple C-seed or one single 128-bit SRv6 seed in it. So in G-SRv6, different types of G-seed can be encoded into a single SRH. To indicate that the next seed is a C-seed, we need to define a new flavor. We call it as continuation of compression flavor. And it is also called replace C-seed flavor, defined in SRv6 compression draft, which has been adopted by IETF Spring Working Group. When processing a seed with CLC flavor, a node will use the next C-seed in the seed list to update the C-seed in the destination address field instead of updating the 128 bits in the DA as the normal SRv6 processing. So in order to locate a C-seed in the seed list, we need to define a new term called seed index to identify the location of the C-seed in the G-seed container. The SI field occupies the least significant bits of the argument field in a seed. Similar to locating a seed through the SL field, we can locate a CSID through the SL and SI fields. The processing of CSID flavored seed is very simple. When a node receives a seed with a COC flavor, it checks the SI value in the destination address. So if the SI value is greater than 0, it means that there are some CSIDs in the G-SID container to be visited. So in this case, the SI value is decremented by 1 to point to the next CSID. And then it will be updated to the DA with this CSID and then forward the packet. If the SI value is 0, it means that all CSID in the G-SID container have been used. So we need to get the next CSID in the next G-SID container. In this case, the SL is decremented by 1, point to the next G-SID container. In addition, the SI field is set to 3 or 7 according to the length of CSID, so that we can find out the first CSID in the next G-SID container. So after locating a G-SID or CSID in the SRH, we can update the CSID to the IPv6 destination address, and then we can forward the packets based on the updated destination address. Here, I will use a simple example to describe how G-SRv6 works in forwarding. Assuming that a packet needs to be forwarded from node 1 to node 9, and they support G-SRv6. The common prefix of seed is a://64, and the node ID and function ID fields are both 16 bits long, but actually it can be like 20 bits and 12 bits. It's up to you. So the argument field is 32 bits long and all set to zeros. As such, the seeds from a:1:1:1 to until a:8:1:1 are all end seed with COC flavors. And a:9:2 is the normal SRv6 end seed without the COC flavor. So this figure shows the encoding format of the seed list in the SRH. In reduced mode, the first seed a:1:1 is not encoded in the seed list, and it will appear only in the DA. Therefore, the SL field can be set to 2, and the SI field set to 0. When the packet is forwarded from the node 0 to node 1, no one detects that the a:1:1 in the DA is a COC flavored end seed allocated by itself, and then it checks the SI value. Because the SI value is 0 now, so the N1 decrements the SL value to 1 and set the SI value to 3, and locates the next CSID 2:1. And then the node 1 updates DA to be like a:2:1:3 and forward the packets based on the updated DA to the next hop's node 2. So after receiving the data packet, node 2 processes the COC flavor end seed in the similar way. Because the SI value is greater than 0 now, the N2 decrements the SI value to 2 and locates the next CSID 3:1, and then it updated CSID to the DA and then forward the package to the next hop, node 3. This processing repeats again until the packet is forwarded to the node A. So when the packet is forwarded from node 8 to node 9, the node 9 detects that the DA is a:9:2:, which is a normal end seed allocated by itself. So the N9, the node 9 will process this seed as a normal SRv6 processing and end the forwarding. So now we have a basic understanding of G-SRv6, and we can see that the G-SRv6 has multiple technical advantages. First of all, G-SRv6 is compatible with SRv6. It supports smooth upgrade from SRv6 to G-SRv6, and it does not change the SRH encapsulation format at all. Secondly, G-SRv6 supports efficient compression and large-scale network deployment. Using 32-bit CC or G-SID, the G-SRv6 supports large-scale network deployment and reduces SRv6 seed least overhead by up to 75%, which keeps the best balance of scalability, efficiency, compatibility, and flexibility. And if you're using 16-bit G-SID, then the compression can be better. The third one is that G-SRv6 supports flexible address planning, consuming fewer addresses. It can provide stable compression regardless of the prefix type and length, and it allows operators to plan the G-SRv6 seed space based on their own IPv6 address without any specific or special requirement. And also we can avoid readdressing in the future. Since G-SRv6 will not introduce new extra rules, security policies, and even new address comparing to SRv6, so we can smoothly upgrade the live network even from SRv6 to G-SRv6. With the best balance of scalability, efficiency, compatibility, and flexibility, G-SRv6 can help you to enjoy the benefits of network programming with much lower cost for today and the future. Thank you.